following on from the work in accurate unlexicalized parsing, there was then an extension which led to latent variable PCFGs, which I'm not going to go through in detail, but I just want to briefly introduce the idea of and show you how it works. So in the model that we were looking at previously for accurate unlexicalized PCFGs, everything was hand done. Someone was staring at sentences and how they parsed and deciding how better to split the categories to build a parser that would work better. So if you're interested in machine learning, you should be thinking, gee, maybe we could do that automatically rather than doing it all manually. And so that's the idea of latent variable PCFGs. So the starting point is we still have a tree bank to train on. So the bracketing of the sentences and the training data are known, and the base categories are known, so that we have a noun phrase node that's in some context, and we already know that. But what we're saying is, well, maybe there's some way that we'd like to annotate it with more information to say what kind of a noun phrase it is so we can parse more accurately. And so concretely, the way that's being done is by splitting the noun phrase category into a certain number of subcategories where each one is just being given a number. So this is an NP17. And so then the learning task is to choose both a number of subcategories and then how to group all of the noun phrases into in the training data into particular subcategories so that you can have something in common in all the NP17s so that you can then have good predictions as to how they expand and which words they contain. And I'm not going to go through that algorithm in detail. If you've seen things in other classes like machine learning or probabilistic graphical models, it's a form of the EM algorithm, like the forward-backward algorithm used for HMMs, constrained by the pre-existing tree structure. So what you're doing is you have the pre-existing tree structure in black, and you're wanting to have a probability distribution over different latent substates of each category. And the simplest way of doing this would just be to say, okay, each category has 10 subcategories, and then learn a probability distribution over the choice of different subcategories for the S state. But that had been tried previously and not been found to not work very well. So what Slav Petrov introduced was a cleverer split merge algorithm where for each category you started with just the single category of an S, and you said, okay, let's try and split that into two S categories. Is there a good way to split it to capture more conditioning information? Yes, let's keep that split. Okay, well, try again. Let's take each of those and split them into two. And so we have 4 S subcategories. And then maybe at that point you discover that one of those splits was useful and the other one wasn't. So you just get rid of the other one again and go back to 3 S subcategories. And you'd repeat that over a number of times. And so you'd progressively split and merge the subcategories and come out with a good number of sets of different categories. Yeah, again, I'm not going to go through the algorithm in detail. Let's just look at how it turns out. So this shows some of the subcategories that are learned for part of speech tags, because they're the easiest ones to interpret. So this is for proper nouns. And so what we find is that the proper nouns have been divided into groups. And the way they're divided isn't just purely syntactic, like a feature-based grammar anymore. They're kind of syntactico-semantic class-based models. So we have a subcategory of proper nouns, which is abbreviations for months. We have another one that's first names, another one that's initials, another one that's last names of people. And then we have 2 corresponding states here for what are location names, which are multi-word, and again we have a first word here and a last word here. So we have these kind of interesting semantic subclasses of nouns. And something similar to that is happening also with the personal pronouns. So we're having the ones that are the nominative subject pronouns, and we're having the ones that are the accusative object pronouns, and then we're also then distinguishing between the subject ones as to whether they're capitalized or not, which is maybe capturing something about whether they're at the beginning of a sentence. And a word isn't restricted to only appear in one category. It can be in the rewrite of multiple categories. So it appears in both these places because it's used as both a nominative and an accusative pattern. Looking overall at the pattern of state splits for phrases, this actually works interestingly and linguistically very effectively. So for the common categories like noun phrase, verb phrase, prepositional phrase, but equally the ones where the basic categories of the Penn tree bank were too crude, that's what we found out previously with our hand state splits. We found that we wanted to distinguish possessive noun phrases and we wanted to distinguish verb phrases depending on whether they're infinitive to verb phrases, whether they're ing verb phrases, or whether they're finite verb phrases. Well, in those places, the split merge algorithm learns a lot of subcategories. It's learning 25, 35 or so subcategories. On the other hand, for the rare weird categories, the unlike constituent phrase, the right recursive clauses, the fragments, it's learning very few subcategories. In fact, for these ones over here, it's making no splits at all, and it's just having the single tree bank category. Okay, so we're then building a grammar that is making splits which aren't purely syntactic. It's also got semantically flavored splits, but it's still much coarser than actually doing headword lexicalization. So in the models that I'm showing you here, the maximum possible number of splits that could happen to a category was 64, and in practice only at most a reasonable number of them survive. So in practice you are always getting less than 40, as you can see in this example. So with just that level of state splitting, how well can you make a parser work? And the answer turned out to be you could make a parser that worked amazingly well. So this slide shows you current parsing results for the parsers that are around when I'm saying this around 2012. So we started off again with our basic PCFG at around 72.7% F1. And we're working up from there. And I'm showing two columns of results. A lot of early parser results were shown on sentences up to at most 40 words, whereas more recently it's been more common to show results on all sentences of any length. Okay, so our baseline now is this unlexicalized parser of Klein and Manning, and so sentences of all lengths, it's getting a little bit under 86% here. Matsuzaki et al. Tried the simple idea of splitting each category with latent states, but just assuming the same number of latent states for each category, and that didn't really work any better. In particular, both of these parsers are still noticeably below what you could get by doing lexicalized PCFGs with headwords. So the best of the Charniak-Collins family of lexicalized PCFGs was this more recent model of Eugene Charniak's from 2000, and it was getting 89.5%. And so it seemed like maybe this 3.5% gap was the value that you were getting from lexicalization beyond what you got from this basic state splitting. But what the latent variable PCFG showed is, well, actually you could get all that value without actually modeling particular head words, but just using these fairly coarse semantic classes of words. So the latent variable PCFG is actually a little bit better, and it's getting this extra 0.5% here. You kind of can't explain in absolute versions why it's better because really it's using less conditioning information than Charniak's parser. So the reason it's better is because the probability estimation is better, and it's better because it's actually a lot easier to do here because you have a much smaller number of categories in the grammar and you're not having to do complicated smoothing with head words. Now, people have gone on and done further work with lexicalized PCFGs, and so in particular, Eugene Charniak and Mark Johnson worked together to add a discriminative re-ranker on top of the Charniak parser. So this discriminative re-ranker is essentially using a Maxent model of the kind that we saw in week 4, but applying it now to choose between different parsers for a sentence, where the candidate parsers are being generated by Charniak's generative parser. So this is feeding into that. And while the Maxent model was again able to do this kind of better form of probabilistic conditioning, which definitely helped. So that was then adding about 2% in performance to the Charniak parser, and in particular adding a little bit still above the level of the Petrov and Klein parser, but still noticeably knowing about individual particular head words is still now only giving you about 1.3% in performance. And finally, as always in machine learning contexts, if you have a bunch of systems, a bunch of classifiers for doing things, you can always get even better results by combining them all together. And people have shown that. So Fossum and Knight combined various constituent parsers and their performance into an aggregate model, and that was able to get an extra % of performance. So this is the state of the art at the moment for performance in probabilistic parsing, which is actually an extremely high level of accuracy. Probabilistic parsers actually can give you the right parsers for most parts of most sentences quite reliably. Okay, so that shows the idea of having these latent states. When you allow them to be defined to maximize parse performance, you get these syntactico-semantic states which really allow you to parse rather well, still with a quite compact grammar.